In this video, we're going to look at two problems that involve force equals mass times acceleration and are themed around lifts. These are very common in A-level mechanics for maths, but could equally be in an A-level physics exam. Pause the video now and try question one. So as usual, it's always sensible to draw a quick diagram just to make sure that we have labelled all the forces correctly and have a clear picture in our mind. So let's draw a picture of this lift. Let's draw the box in the lift, which has a mass of 55 kilograms. The lift itself has a mass of 1,000 kilograms. And we have this Lloyd character sitting on a box, and his mass is 55. So the box is 25 kilograms. And then we know that it's moving vertically upwards, accelerating with a magnitude of 2.5 meters per second squared. So part I, we're asked to find the tension in the cable. So what are the forces? Well, we have tension, which is pulling up, and then we have weight pulling down. So what we need to use is Newton's second law, which is the resultant force, or the net force, is mass times acceleration. And this is really what we're going to use for all of the problems. So what is the resultant force? Well, it's accelerating upwards. So the resultant force is tension minus the weight. And that's going to be equal to the mass times acceleration. So the tension is obviously mass times acceleration plus the weight. So now, importantly, we need to make sure we've got the mass correct. Well, it's the tension is lifting the whole of the lift, so it's the combined mass of everything. So the combined mass is going to be 1,080 times by the acceleration, which is 2.5, and then plus 1,080 times the acceleration of acceleration due to gravity, which is obviously 9.8. So let's put this in our calculator. And we get 13,000 Newton. Part II. So in this part, we're asked to find the force on Lloyd in the box. So I've labelled the force of Lloyd's weight, and then we're asked to find the force upwards that is making him accelerate. So again, we can use the same idea that the resultant force is mass times acceleration. So what is the resultant force? Well, it's going to be the force upwards. So I'm just going to use this for the force upwards minus his weight is going to be equal to mass times acceleration. Now, importantly, the mass in each of these is going to be the mass of the thing that is accelerating, not the whole mass. So it's just going to be the mass of Lloyd. So we're trying to find the upwards force. So again, MA plus MG, which is going to be 55, and then he's accelerating obviously at the same rate as the whole lift because it's all connected. And I've just factorised a bracket here just to save a couple of seconds when I type in my calculator. And you can see that the force is 676. I'm just going to round it to 680 newtons. Now that's the force up. We're actually asked of Lloyd on the box. Well, if this is the force upwards that's making him accelerate, by Newton's third law, we know that there is an equal and opposite force downwards from Lloyd on the box. So the answer must be 680 newtons down as well. Okay, finally, part 3, the magnitude of the force exerted on the box by the lift. So similar idea, we're going to use F net is mass times acceleration. What is the resultant force? Well, it's the force upwards on the box minus the weight. I'm going to use big M this time just so I can really make it clear it's going to be a different M. And then obviously the mass of the thing that's accelerating times mass acceleration. So we don't know what the accelerating force is, but we know what the mass is. And again, I can rearrange it in exactly the same way I've done here. So the mass of the thing accelerating is now the box plus the person on top of the box, because all of this is connected and the lift is pushing up on both of them. So the mass is going to be the sum of these two, which is 80 kilograms. Everything is accelerating at the same rate, which is 2.5. And then we're going to obviously use gravity as 9.8. So the force on the box to make it accelerate is 984 newtons. So that is going to be the upwards force here. So what force is down is the box exerting on the lift, but again, by Newton's third law, it must be the same. So the answer is again 984 newtons, or 980 newtons. Question 2 is here. Pause the video now and try this question. So part I, we are asked to find the tension in the cable. So we're going to use basically the same idea as we've used here, but we just have to be careful. We've got everything correct. So we've got 70 kilograms, we've got 60 kilograms, and we've got 80 kilograms. We've got the mass of everything times gravity, that's the weight of everything pointing down, and we've got the tension pointing up, and then the lift itself is 950 kilograms. Now it's descending vertically downwards with a constant acceleration of 1.6 meters per second squared. So in these examples here, it's going up, and we've always said it's the tension minus the weight, but here it's going down. So we need to make sure the resultant force is expressed correctly. So it's mg minus the tension is mass times acceleration, and therefore mg minus ma is the tension, which is going to be the mass of everything, which is 80 plus 60 plus 70 plus 950, which is 1160, and then 9.8 minus the acceleration, which is 9,500 newtons. Part II, the force on B from C. So the resultant force on B is again mass times acceleration. So the resultant force is again the mass, let's use a capital M to show it's a different mass, times gravity minus the upwards force. Now I'm not going to say it's tension because it's obviously the contact force from A pushing up. So let's just go the upwards force equals mass times acceleration. So we obviously know what the mass is because we've got the masses. We know what gravity is. We don't know what the upwards force is, right? Because it's not necessarily the tension. This mass is the same as this. And acceleration we do know because it's obviously the same in every single part of the question. Everything is accelerating at the same rate. So let's work out what the upwards force is. It's going to be mg minus a, and it's the force on B from C. So I've just made a slight mistake. I should have obviously put mass C here because that's the thing we're looking at. And this upwards force is the upwards force from B. Otherwise, everything is still correct. So if we can find this upwards force here, then we know that the downwards force will be the same by Newton's third law. So the mass of the thing accelerating C is 70, and then the acceleration is still 1.6. So the resultant force on C is given by this, and it will be the same as the force from B on C. So let's figure out what the answer is. 574 newtons, which is considerably less than this, but you would expect that because we're only looking at a very small mass compared to the large overall mass. Part 3. The force on B from A. So we're going to use basically the same idea here, but we're now looking at the force on B from A. So this contact force here. So what we need to do is find out what the resultant force on B and C are, and then that will be equal to the normal contact force from A on them. So we're going to use the same expression here. So the force from A on B is going to be equal to the mass of both B and C, and then obviously our common factor here. So we've now got a mass of 130, right, because both of these things are on top of A, so obviously both of them are pressing down on A. And then 9.8 minus 1.6, because everything's accelerating at the same rate. Which is 1,066 newtons, or I'm just going to round that up to two significant figures. Probably should have done that here as well. Part 4, the force of A on the lift floor. So we're going to repeat exactly the same calculation now, but we're going to work out what this pair of forces is here. So we want the force of the lift on A. It's going to be given by the mass of A, B, C, G minus A. So the mass of all of these together is 80 plus 60 plus 70, and then times by 9.8 minus 1.6, which is 1,700 newtons. So that is both the resultant force on A down and the contact force up. And then finally, in part 5, we're now at a constant velocity of 0.5 meters per second. What are the new answers? So now we're at a constant velocity, so A is 0. So these answers simply just become the weight. We can imagine it's stationary. And if it was stationary, it would be a really, really easy problem to solve. So the force on B from C is obviously just the weight, which is weight is mass times gravity, so 70 times 9.8, which is 690 newtons. The force on B from A, so again, we're going to do 70 plus 60 times by gravity, which is 1,274 newtons. That will be the same as the force up. And in part 4, A on the lift floor, well, it will be the weight of all three of these. So 80 plus 70 plus 60 times 9.8. I've done that wrong. 80 plus 70 plus 60 times 9.8, which is 2,100 newtons. That's the force down and the force up. And you can see that in each of these cases, the force is larger than it was before, which makes complete sense, right? Because it's moving at a constant velocity. It's no longer accelerating. When it's accelerating down, the downwards force must be greater than the upwards force in order to make it accelerate, which means that all of these forces should be smaller, because otherwise it wouldn't be accelerating.